So the only new thing we learned yesterday is that first formula that I have there. Electric field strength is voltage over distance between the plates. You want to be very careful looking at some of those formulas because three of the formulas have E's in them. Wetaskiwin tap water. Actually, school tap water. It's even worse. Three of those formulas have E's in them, and you need to be careful about what those E's are. In the formula at the bottom of the screen, that energy is electric energy, or I guess kinetic energy. But it's energy. That's maybe what I should have said instead of even using the word electric. That E at the bottom of the screen in your voltage formula is energy, whereas the capital E with the vector symbol above it in the equation to the left and the equation to the right, those stand for electric field strength. And again, regardless of what your formula sheet says, this formula on the right is written a different way. It's written, I believe, as electric field strength equals, but I think it serves you better to put absolute value signs around it. I think it's wrong to leave them out. When you have a charged particle in an electric field, it's going to experience an electric force, and that electric force very often is the net force, which can be used to find an acceleration if you want. Some of these questions that you were assigned, you are probably going to have questions with because they are tied to example number 3, which we didn't do yesterday. So let's open it up. Does anybody have any questions you would like me to go over? Ian? Okay, let's take a look at number 12. We're asked to find the potential energy, the potential difference. And Ian, you and I had a lot of discussion this morning about, the importance of the language here. This is potential difference. It's not potential energy. It's potential difference. And potential difference is voltage. And voltage, that's what I wanted to tell you. I put those little caps on the V just to signify that it's a capital V. I hope you don't misinterpret that to mean it's a vector. It's not a vector. Voltage is a scalar. Is change in energy over charge. And I've said this before, and Ian, you and I talked this morning about this, but I will say it again. Any formula that's on your formula sheet is only good for standard units unless you're told otherwise. Which means in this formula, this is volts. So what I'm writing in red are the units. This is energy, which is joules. And this is charge, which is measured in coulombs. So I'm abbreviating the unit, but I'm also writing what the name of the unit is. So when you use this formula, you have to use those units. Now, if I'm asked to determine the voltage, then I need to put in the energy and the charge. Well, it's a proton. I know the charge of a proton. You're told it's going to get a kinetic energy. You're told you're going to get a kinetic energy of 2.8 times 10 to the 6 electron volts. That's energy. But we cannot put that in for the energy unless we put it in joules. I mean, make no mistake about it. This is a change in energy. It's just got the wrong units to make this formula work. So we have to take 2.8 times 10 to the 6 electron volts of energy and convert it to joules. And I'm going to ask the question for the third time. I know it's the third time. You are told on your formula sheet that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. To how many of you know exactly what you have to do to this many electron volts to find out how many joules it is? You multiply, right? And this is what I was talking about with Ian this morning, is that really this is equivalent to saying 1.6 times 10 to the negative 19 joules per electron volt. That's what it is. It's just a conversion factor. If you cannot convert that many EV to joules intuitively, then you're going to set up a ratio. You're going to say, I would write 1.6 times 10 to the negative 19 joules over 1 electron volt equals x joules over 2.8 times 10 to the 6 EV. This is kind of like if you had me for Math 20 and you're using the sine law. Anytime you set up a ratio, the thing you want to find, put it on the top. It just makes it easier. So I've flipped my ratios over. If we do that, 1.6 times 10 to the negative 19 joules per electron volt multiplied by the 2.8 times 10 to the 6 electron volts gives me 4.48 times 10 to the negative 13 joules. Is that right? Did anybody else get the same same number? Okay. So now what we can do, Ian, is we can put that into this formula that is kind of hidden, camouflaged by everything else, so I will just highlight it. We're going to put that energy into this formula along with the charge of the proton. How many of you see what's going to happen here? Okay, I'll come back and explain what I'm talking about in a second. But we want to calculate the voltage, and we have that change in energy of 4.48 times 10 to the negative 13 joules, and we're going to divide by the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs. Now, just a second here. When you converted those electron volts of energy to joules, you multiplied by this number. Now, you happen to multiply by that number of joules per electron volt, but regardless, you multiplied by that number. And now, when we put it into the formula to calculate the voltage, we're going to take the result of that multiplication and divide by this number. It's coulombs this time, but we're dividing by the number. And what we get is the original number we started off with, which hopefully will make sense. We get 2.8, wow, we get 2.8 times 10 to the 6 volts. And the reason it makes sense is if 1 electron volt is the energy gained by 1 electron accelerated through 1 volt, then this many electron volts is the amount of energy gained by 1 electron accelerated through this many volts. I'm aware it's not an electron, but a proton has the same charge of an electron. And that's what determines the energy. It's the charge, not whether it's a proton or an electron. So that's the answer. Other questions? Yeah. Certainly. You said 6? This is one of these cases where something changes. We're beginning to see them more often than not. So what we're told to begin with is the initial state of things is we have an electric field strength with a magnitude of 930 volts per meter, and the distance between the plates is 0.07 meters. And what we are asked is, afterwards, you can use A and B or I and F, whatever you want, is what would the new electric field strength be? Bless you. If the distance between the plates were reduced to 0.05 meters. And by the way, I know some of you like ratios. The ratio is not going to help you here because it's not a proportionality. When the distance gets smaller, the electric field strength will get bigger. What we want to do here, Shannon, is identify the equation that relates all of this. How is the electric field strength determined from the distance between the plates? Well, it's determined by using this formula. Electric field strength is voltage over distance. And in this question, in this situation, these things change, but this is constant. Now, after I go through this, I'll show you a specific way we could do this question instead of this. But what I'm showing you is a way to do all questions like this. And the specific way won't always work for all questions. So if I cross multiply here, I can write that the electric field strength multiplied by the distance between the plates is equal to the potential difference. And I shouldn't just assume something here. When we read that question, it never mentions changing the voltage, right? If there's an electric field strength and you have two plates, there must be a voltage between the plates. All it says is we change the distance. So if it doesn't mention the voltage, we don't assume it changes. The key idea here is that if this is constant, which it is, it doesn't change, this must be constant because it's equal to the voltage. Now, I mean, the electric field strength is going to change, the distance is going to change, but they're going to change in such a way, either do that or do that. One will get larger, one will get smaller, so that they stay the same. And what that means is we can take the electric field strength times the distance to begin with, set it equal to the electric field strength times the distance afterwards, and get the answer to the question. So if we put in, what was it, 930 multiplied by 0.07, that's going to be equal to the new electric field strength multiplied by 0.05. And you can finish the problem now. You know, what you could have done is you could have just calculated the voltage using the information to begin with, and then use that voltage and the new distance to find the new field. But that only works if you have one variable that's constant. If I had a whole bunch of variables that are constant, it doesn't work. Other questions? Yeah. Sorry, way back? 11? Okay. So the momentum of a 6.5 electron volt alpha particle. Well, momentum is calculated using mass times velocity. So if we want to find the magnitude of the momentum, and this question probably should say what is the magnitude of the momentum, we're going to have to take the mass times the speed. And we know the mass of an alpha particle, but we don't know the speed. However, from here on in, when we're talking in physics about the energy of a particle, not a car or a baseball, we're assuming we mean kinetic energy. So when I say we have a 6.5 eV alpha particle, that means the kinetic energy of the alpha particle is 6.5 electron volts. And I would like everybody right now, whether you did this question or not, to convert that to joules. And I would go so far as to say it should be coming very natural. Should be very, very natural to know what to do here. That's what I get. And again, I'm not trying to push you so far that you're not successful, but I think if you have to stop and write out 1.6 times 10 to the negative 19 joules over 1 electron volt equals x joules over 6.5 electron volts every time, it's going to slow you down. I just multiplied by how many joules there are per electron volt. And I'm going to go on the assumption right now that everybody can find that. Okay? If you're having difficulty with this conversion, then we need to sit down together and have a conversation. Now what I can do, and the reason why I'm doing this way, Ben, is kinetic energy is 1/2 mv squared. This equation is my vehicle for finding the speed so that I can find the momentum. But that equation only works if I use joules. So now what I can do is set that 1.04 times 10 to the negative 18 joules equal to 1/2 mv squared. There, I'm not really keeping track, but that's probably at least the 10th time we've used that formula in 2.5 days of classes. We're going to take that energy and multiply by 2. That was right, wasn't it? 1. Okay. And multiply by 2 to get rid of the half in that equation and divide by the mass of the particle that we're talking about, which is an alpha particle. And that has a mass of 6.65 times 10 to the negative 27, pretty sure. Hit equals and take the square root. And what we've found now is the speed of the alpha particle. And if I want to know the momentum, then I guess I have to multiply by the mass. So I'm getting 1.2 times 10 to the negative 22. Now some of you might kind of say, well, we divided by the mass and then we multiplied by the mass. Did we really have to do that? And the answer is yes. Because when we divided this by the mass and then took the square root, we actually ended up dividing by the square root of the mass. So it isn't like things kind of balance out. You need to actually do these calculations. There's no zippy shortcut to the answer here. Any other questions? I thought somebody else said, but I didn't know who was speaking. Yeah. 8? So you're asked for the electric field strength 1 centimeter from a positively charged plate if the two plates are 5 centimeters apart and the potential difference between them is 300 volts. Well, electric field strength for parallel plates is given by this formula. And this is why I mentioned yesterday, I really dislike that delta. I think the delta is, I wish we had something different there. In this formula, this is the distance between the plates, period. So I need to take 300 volts and divide that by the distance between the plates, which is 0.05 meters, and that's going to give me 6,000 volts per meter. I've got this diagram up here to remind you that this is what the electric field lines look like between parallel plates. And the fact that they are parallel field lines means they are equally spaced, which means the electric field is the same everywhere. So if I said, what is the strength of the electric field here or here or here or here, it's the same everywhere. And this is there just to confuse you. Good. Any other questions? 11? 7? So I have a field. Situation 1 has a field because of this. This is the source of the field. It's a point source. Whereas over here, the source are these two plates. Oh, I'm sorry. You're right, you said 7. So this is the same kind of thing as the question Weiben asked about, but we're not going to go as far. In Weiben's question, we were asked to find the momentum of a particle given its energy. So in this particular case, you're just asked to find the speed given its energy. And again, at this level, when we talk about particle physics, and we talk about things like electrons or protons or even atoms, If I just say it has that much energy, I mean it has that much kinetic energy. So in order to find the speed, we have to take this energy and put it in here to get the answer. However, along the way, we have to convert that to joules. Right? We need to convert to joules in this direction. So what do we have? We have 13.3 EV. Again, I'm going to kind of force you to figure this out if you haven't got it already. Since 1 electron volt is 1.6 times 10 to the negative 19 joules, we're going to multiply that by that number to get the joules. I mean, I don't want to leave anybody in the dust here. If you have to do this, if you have to physically write down a ratio to figure out how many joules it is, then do so. But I'm also kind of cautioning you that hopefully that necessity of doing that is going to fade away over time. It should. So 13.3 times 1.6 multiplied by 10 to the negative 19. This is not coulombs, it's joules per coulomb. Try that again. 13.3 multiplied by 1.6 times 10 to the negative 19 joules per electron volt, rather, gives me this many joules. And now I'm simply going to calculate the speed from this formula. And what I will say to everybody again is that, is it an electron? Yeah. 9.11 multiplied by 10 to the negative 31. Is that you'll notice that as time goes on in this course, we're doing more and more of the work just on the calculator. Because that's math. The physics is what I've written on the board here. You know, and you may have to write down some things, but if you're working on a multiple choice question, I don't think you really want to have to write down all your substitution. I think that's a waste of time. Valuable time. All right, we're going to move on now. We're not going to do example 3 from yesterday because I want to make sure we get to the heart of the matter today. So you're going to need to open up your books to the next lesson, which is on, I believe, page 43 of your unit handout. Okay. We're going to be looking at two things today. Applying conservation of energy to charged particles in electric fields, but we are also going to be looking at the most important thing, which is two-dimensional motion of charges. And just before we get started, how many of you recall from Physics 20 doing those problems where you had an object that rolled off of a table and you had to maybe find out how far from the table it landed? Or how long it's in the air, or if you knew where it landed, how tall the table was. Essentially, when we do two-dimensional motion of charges, it's the exact same situation, except instead of gravity causing that arc, it's an electric force. Okay. To begin with, a quick question here. Let's dissect this. There's a lot of words here. We've got an object. It happens to be a pith ball. There's no way that that's 2.4 times 10 to the 4. I really hope that yours says 2.4 times 10 to the negative 4. Okay. It is not a 24,000 kilogram pith ball. Okay. There's a negative there. It has a positive charge. The charge happens to be positive 1.2 times 10 to the negative 8 coulombs. And it's sitting in an electric field. Now, we don't even need to draw anything just yet, but if I have a charged object in an electric field, it's going to be influenced. And if I release that charged object, it's going to move in the direction that it's forced. Are you with me on that general idea? So there's going to be a net electric force acting on it. It's going to accelerate. But if the particle accelerates, it gains kinetic energy. Where does the kinetic energy come from? Potential energy. This particle sitting at this point must have potential energy. Because if there's a force acting on this particle, and I don't want you to draw anything just yet, but if this is the particle at that point in space, at point A, and it has a charge, and it's in an electric field, there will be a force on that particle. So if it's just sitting there, I'm holding it back. And I can feel that there's a force in my head. I can feel there's a force. Just like when I pull back a rock in a slingshot, I can feel something, which means the rock has potential energy. Just like when I lift this 3-hole punch above my head, I can feel a force of gravity pulling down, which means there's potential energy. The slingshot rock has elastic potential energy. This has gravitational potential energy, but the charge has electrical potential energy. And you are actually told at that point it has that much electrical potential energy. You release it, of course it starts flying like the rock would, or the 3-hole punch would move. And then you take a snapshot when it passes point B, and at point B it has this much potential energy. And with that explanation, I can see some of you already know where this is going. If I want to find out how fast the thing is moving at B, I need to know its kinetic energy at B. And its kinetic energy at B must be the difference between these two numbers. Here's a picture that might help you understand this in terms of a pendulum. If I told you that the pendulum had 70 joules of potential energy here, and down here, at this point, the potential energy is 30 joules, then that must mean that the kinetic energy is 40 joules here, because the total energy has to stay the same. By the way, I'm assuming it's not moving here. This is the highest point. So in this question, all we have to do is say that the total energy at A equals the total energy at B. This is a potential energy at A, and at B, there's a potential energy and a kinetic energy. And I realize that some of you just understand we have to subtract those two energies given to get kinetic energy, but I'm formalizing this. So if I take 3 times 10 to the negative 7 joules at A, that's potential, equals 1.5 times 10 to the negative 8 joules at B, that's potential. I can use that idea to find the kinetic energy at B. And I want to say you're going to get 2.85 times 10 to the negative 7. So when you subtract to solve for the kinetic energy that this object has at B, you get 2.85 times 10 to the negative 17 joules. We're back to this formula, EK equals a half mv squared, where you know the kinetic energy. It's not an electron, so be very careful here. It's an actual pith ball with that mass of 2.8 times 10 to the negative 4 kilograms. And because it's that, I'm going to actually show my substitution here. We have 2.85 times 10 to the negative 17 joules equals 1/2 times the mass. Was my memory right? 2.8 times 10? Yep. Negative 7. Thank you, Annalie. And is it 2.8 times 10 to the 4? Negative 4. 2.4 times 10 to the negative 4. Times v squared. Have I got the numbers written down correctly now? Okay, so now it's just a matter of you solving that. You take the energy times 2, divide by the mass, take the square root. Well, 0.049 meters per second or 4.9 centimeters per second. Okay, that's the answer. Any questions with that example? All right, now the important part of the lesson. So for the first part of this example, you're not going to worry about writing a lot of stuff down. You're just going to pay attention. I have an electron. You can see the electron in the bottom right corner. Does my diagram match your diagram in every way? Orientation, all that. Okay. And it's fired to the left at this location. First of all, the mass of an electron is very wee. It's very tiny. We would never consider the gravitational force on these particles unless we were told to. So we're neglecting gravity because it's not important. In the cathode ray tube here, when you have an image, and I'm going to hook up my laptop next week and show you a demonstration with it, but when you have an image here and the electron gun at the back is firing the electrons around, it's not pointing up because the electrons are going to curve down because of gravity. The amount of time it takes the electrons to travel to the screen is so small, and the gravitational force is so tiny, it doesn't curve. Okay? It's the electric field that's going to produce an electric force that's going to cause some motion. First of all, the top plate is positive. The bottom plate is negative. I think we all know what the electron's going to do. It's not going to do what I call Wile E. Coyote physics, where Wile E. Coyote goes out over the edge of a cliff, looks around, and then goes straight down, right? What the electron is actually going to do is from this point where it enters the electric field, it's going to be curving upward. And it's going to smack into that plate. What we are asked is to describe the path, and I suppose we could just draw it, but there's something else that I need to talk with you about. And that's the physics of the path. And I didn't teach any of you Physics 20, but this is the same kind of way I would teach projectile motion in Physics 20. Except, of course, this particle's curving up, right? Okay. So you're going to have to decide what you want to write down here, okay? But my preference is that you really think about this as opposed to maybe writing anything down. It doesn't matter where the electron is. Once the electron is between those plates, this is a fact. There is only one force acting on it. And just let that sink in. The electric force on this electron will be towards the positive plate. Would you agree? Okay. And that is the only force acting on it. This is a misconception that people have. The electron might be moving at 10 million meters per second to the left. There is no force to the left. The force is towards the top of the page. Just because something is moving in a direction doesn't mean there's a force on it in that direction. It just happens to be what the speed is. If there was a force acting in that direction, then it would speed up, and it's not doing that. It's not speeding up this way. When you look at that force and you think back to Physics 20 about components, and I said, what is the horizontal component of that force and what is the vertical component of that force? However many newtons that is, that's the vertical component. The whole force is the vertical component. None of that force is in this direction to the left, and none of the force is in this direction to the right. It's all up, exactly. And that's an important idea. The horizontal component of this force is 0, which means there's no horizontal acceleration. So if I tell you that the particle enters the field traveling to your left at, I'm just going to choose a really stupid number, at 2 meters per second, and the plates are kilometers apart, that means it's going to continue to travel to the left at 2 meters per second, forgetting about what it's doing this way, up and down. That will do that. 1 second later, the particle will be 2 meters to the left. Another second later, the particle will be another 2 meters to the left. It will also have traveled up, but it's going to travel at that uniform speed horizontally. So I realize now that when I say this physics principle is that of balanced forces resulting in uniform motion, I'm talking about the horizontal motion as uniform motion. All this stuff in blue that I've referred to a couple of times in this course, and we're going to refer to more and more, is what's going on horizontally. The net force on the particle horizontally, the net force is 0. So it can't accelerate horizontally. However, the vertical component of that electric force is, as we already said, the entire electric force. So that means there's a net force vertically towards the top of the page or the top of the screen. And that means that the particle will accelerate, because if you look at the pink sheets, that's non-uniform motion because there's an acceleration. Specifically, it's this yellow section. In Physics 20, you learn that there are two general types of acceleration. Acceleration in a straight line where you either speed up or slow down, or centripetal acceleration. The green sheets describe everything that's going on with centripetal acceleration. The yellow is linear. So the yellow and green sheets on my bulletin boards are the pink sheets splitting into two different things. They are both accelerated motion. But what's happening is linear acceleration vertically. So if you take a look at the particle when it first enters the field, there is no vertical velocity. And that's something different than the force. The particle is entering this way. It's not angled up, it's not angled down. Do you remember in Physics 20 that you do projectile motion where the objects are launched at an angle? We'll never see that here. The analysis is too complicated, okay? But there is a horizontal component to its velocity. Whatever it is, if it's 2 meters per second or 2 million meters per second, there is a velocity component. A short time later, the velocity component that's horizontal will still be the same. I really want that to sink in, that this velocity Vx here and this velocity Vx here are the same. It hasn't increased, it hasn't decreased. But look what's happened to the vertical component. All of a sudden there is a vertical component. And if we look the same time later, the vertical component will have grown a little bit more because it's accelerating vertically. The horizontal will stay the same. And this is what ends up happening. And that's why the particle doesn't travel in a straight line, either at an angle or horizontally. It's because the vertical velocity is always growing. And the end result is that you get a parabola. So the answer to this first question is we get parabolic motion. And you will be asked on exams potentially to name the type of motion. It's parabolic or parabolic, as opposed to circular. This is not circular motion, it's parabolic. And what that means is if you graph this, you could create an equation by talking about x squared. Okay. So this is the same as a rock thrown horizontally from the edge of a cliff, except that, of course, when that happens, it looks like that, right? And the force is not an electric force, it's a gravitational force. And when you solved these problems last year, you always solve them the same way, and I really hope you remember this, that you create a chart that has horizontal motion and vertical motion, and you treat them mathematically separate from each other. And that's what we're going to do here. So let's take a look at the next example, next part of this question, rather. If the electron experiences an acceleration of 2 times 10 to the 16 meters per second squared, and the plates are 4.5 centimeters apart, what's the voltage between the plates? So this acceleration is vertical. Right? It's towards the top plate. 2 times 10 to the 16 meters per second squared. This distance between the plates, which is delta D in our electricity formulas, is vertical. Right? The plates are here. The distance between the plates is 4.5 centimeters. And that means that we don't have to worry about the particle's motion horizontally. We can treat things vertically. And you're going to have to get used to, in this lesson, jumping around from formula to formula, because there's a whole bunch of them that we need to use here. So how do we find the potential difference? Well, There are a couple of ways, but what I will tell you is, in all of these questions, never use this formula. Okay? Ever. There is an exception, and some of you might stumble on it later, but I don't want you to. Okay? Unless you figure it out. So the only formula we can use here is electric field strength equals voltage between the plates divided by distance between the plates. And here's the problem-solving tool or strategy I want you to take in all of this today. This voltage is what we're trying to find. What in this equation is preventing us from finding the voltage? The electric field strength. We don't know the electric field strength, but electric field strength is electric force divided by charge. So if we can find the electric field, we can calculate the voltage. Okay, that's great. But when you look at the formula I just wrote down, something in this is preventing us from finding the electric field. And it's that we don't know the force. But the electric force is the net force, which is equal to ma. Now we're getting somewhere. Because I know the acceleration and I know the mass, so I can calculate the net force. That's the electric force. I can divide that by the charge to get the electric field, and then I can multiply that by the distance to get the voltage. And what I would tell you is, all of these formulas are little chippy formulas. 3 variables, and there's a fraction someplace maybe. To solve for any of these variables is easy. I'm not even going to write anything down. Let's calculate the force. Let's take the mass times the acceleration. It's an electron. So the mass is 9.11 times 10 to the negative 31 kilograms times the acceleration of 2 times 10 to the 16. This is the acceleration. And don't forget, we are finding the acceleration. Sorry, that's not the acceleration. This is the force, the net force. And we are finding the net force so that we can put it in here to find the field so we can put it in here. I misspoke when I said that was the acceleration. It's obviously the force. So now I'm going to take that force divided by the charge to get the field. Okay, so that's the electric field. And now I can put the electric field into that other formula, multiply by the distance between the plates, which was it 4.5 centimeters? Yeah. Of course, we have to use standard units of meters, so the answer to the question is 5,124 volts. And things are going to get more complicated. We've got a little trail of breadcrumbs here to follow that has 3 breadcrumbs. It can be 5, maybe even more. Okay. All right. Let's take a look at example 3. And question number 3, everybody. I want to go relatively slow here so that I set it up so that we don't have to spend a lot of time writing. But question number 3 is one of those 1-2 physics principle punch questions, where you're given a complicated problem and you have to numerically calculate something, and then you use 2 physics principles. So An electron enters the region between the plates with a horizontal speed of that. The plates are 5.6 centimeters apart and 13 centimeters long. What is the maximum voltage between the plates that the electrons will just clear the plates by? Just looking up here, do you agree that if the voltage were 10 million volts, this electron is likely to do that? Okay. Do you agree that if the voltage is a millionth of a volt, that might be the path of the electrons? What we are after, and I'll see if I can nail this, what we are after is that. We are after the path that the electrons just miss the bottom plate. Okay, now how do we do this? Don't rush to write all this down. I want you to think about what this is. Since the horizontal motion is uniform motion, the only formula you can use with any horizontal components is the uniform motion formula. Speed equals distance over time. Since the vertical motion is accelerated, we have all this kinematics stuff, to be kind. All of that VI, VF, AD, and T that you dealt with last year. And we are going to have to deal with kinematics here. But we also have net force equals MA, electric force equals QE, electric field equals voltage over distance. Notice that what I've done here is I've put two kinematics formulas up here because there is no horizontal velocity. Sorry, there is no vertical velocity to begin with. I guess I had that. That VI here is under the vertical column. And when you look at the original path of the particle, it's moving horizontally. There's no vertical motion to begin with. Are you with me on that? This will always be VI equals 0 in the vertical side. This formula is actually, you don't need to write this down at all. This formula is actually this. But since VI is 0, it's that. This formula is actually D equals VIT plus a half AT squared. But since VI is 0, it gives you that. These are the two formulas you're most likely to make use of. So let's look at the question. The question is, and get ready for it, the question is, what's the voltage, right? So before we drop our breadcrumbs down, let's label some things. Was it 5.45 times 10 to the 6 meters per second? What else do we know? Oh, we know the distance. Wasn't it 13 centimeters long? That's a horizontal distance, so I'm going to put that here. We know VI is 0. We also know the distance between the plates, which is a vertical distance. And the vertical distance was 5.6 centimeters. And that's it. So, think about this. We want the voltage. What is preventing us from finding the voltage? Well, we don't know the electric field. But we can calculate the electric field from this formula, except we don't know the force. We can calculate the force from this formula, but we don't know the acceleration. If we knew the acceleration here, we could put the acceleration here, calculate the force, calculate the field, calculate the voltage. But we cannot, this is our new goal, we cannot find the acceleration knowing only two other kinematics descriptors. You always need to know 3 kinematics descriptors to find a fourth. So now the question is, how can we find the acceleration? The answer is you find the time. And I hope this is stuck in your head from last year. With projectile motion, even though you solve things horizontally separately from vertically, the time is the same, isn't it? Okay. So here's what you have to do. You have to use this information to find the time. And I know some of you are anxious to get an answer here, but you have to use this to find the time. Then once you get over here, I guess we can use d equals a half at squared to find the acceleration. Then you can find the force. Then you can find the field. Then you can find the voltage. Like 5 or 6 breadcrumbs. So that's what has to happen here. You need to calculate the time first. And by the way, I've rearranged your speed formula. It's v equals d over t. You need to use d equals a half at squared to find acceleration, and that's rearranged. Once you know the acceleration, you can find the force. Once you know the force, you can find the field. Once you know the field, you can find the voltage. And I have all of the numbers up here, and I'm going to let you do the work right now. We'll take 3 or 4 minutes here, 4 or 5 or whatever, and work out the answers. Can I just look at your handout for a second? I will reveal the answers a bit at a time. Once you have your final answer, can you put your hand up? I'm not expecting any hands to be up yet, but. And when I say that, I just mean put your hand up and down so I can just see that you got it. This is illustrating the hands are starting to go up and down now. This is illustrating my point earlier of writing down all these numbers is going to be a huge waste of time. If you understand the physics, the formulas are right in front of you. The numbers are on your formula sheet. I mean, don't get me wrong. I believe it's important that you either write this down or are able to, in your head, keep X separate from Y. I think that's crucial here. That's the physics. So I'll reveal now that my acceleration ends up being 1.97 times 10 to the 14 meters per second squared. When I multiply by the mass of the electron, that's what I get for the force. Perhaps one of the frustrating things here is there's so many calculations and so many numbers to keep track of. It's reasonable to expect anybody to make a clerical error. To understand the physics perfectly, to understand the math perfectly, but to have your finger slip on your calculator and hit the wrong key. Or look at a number in the question and see the wrong number. For that reason that there's so many numbers and steps, you want to go slow and methodical. When I take that force and I divide by the charge to get the field, I get an electric field of about 1121 volts per meter. And then when I multiply by the voltage, I get 63 volts. So how many of you got the right answer? Okay. Okay, good. And I know a few of you are still crunching some numbers, and that's fine. If you did not get the right answer, I'm not going to go through all of these calculations up here because it's just going to take too long. I'll come around and I'll help you in a bit. I think we'll only just finish this one example. I don't think we need to do a second one. I might talk about the second one. But while I'm giving everybody a second to finish that up, I want you to consider what two physics principles you used and in what order you used the physics principles in. I mean, you got a chart that has x and y, and we've said x is uniform motion and y is uniform acceleration. Uniform motion is physics principle 0. Uniform acceleration is physics principle 1. So 0, 1 would be what you would record. Because we did the uniform motion calculation first. 0, 1 would be what you would record. Ian?
Don't we also use conservation of momentum?
No. Nowhere, this is what's very important, nowhere did you use conservation of momentum. Okay? Could you say momentum is conserved here? Well, first of all, momentum isn't conserved because the speed of the particle is growing. Okay? But somebody might, I know where you're going with this, I think. Somebody might say, well, isn't energy conserved? Doesn't potential energy change to kinetic? Yes. But did we use conservation of energy in any of our calculations? The answer is no. So you want to be careful and apply the physics principles that you used, not physics principles that describe what's happening. Okay, I'm going to do one more part to this question. So the two physics principles are 0, 1. Question C says, what speed will the electron be traveling at when it leaves the region between the plates? And D says, what angle will it be traveling at? So if I go back to my diagram, right here, at this point right here, the electron is leaving the region between the plates, and I hope you would agree it's traveling in that kind of direction. Yeah? Roughly. This, you want to be very, very careful about what I'm going to draw here. This is VF of the electron. It's the final velocity of the electron. But that VF, everyone, is not this VF. Let me put it up on the other screen and ask you to just think about that for a minute. I'm telling you that this VF that's on the right-hand screen is not this VF in your table. Why not? Jack?
There's a horizontal and a vertical component.
Right. This VF in the table is only the vertical component of the VF over here. And to be honest, I'm not sure where this arrow came from. Did I just draw that, or was it up there to begin with? Okay. That VF on the right-hand screen, or the VF, let's just go back to reality here, the VF that we're looking at here is the final combined velocity that's a result of the horizontal and vertical components added together. So in this question, we know the object is traveling in this direction. There is a horizontal component and a vertical component. And the horizontal component is that 5.45 times 10 to the 6. That horizontal component is the 5.45 times 10 to the 6 meters per second. This is VF vertically. This is VF really. It's the whole VF. And these two VFs are different. The VF in your table is simply how fast it's moving towards the bottom of the screen. And what we can do here to find that VF in our table is use this formula. This formula will allow us to find the final vertical component, and then we're back to that tip to tail, horizontal and vertical, and using it to find a hypotenuse. Correct me if I'm wrong, this was our acceleration. Okay? So I need to take, using this formula circled in green, 2 times the acceleration times the distance, and take the square root. This is VF. But again, everybody, that's not the final velocity of the electron. That's the final vertical velocity of the electron. So that number of 4.7 times 10 to the 6 is the vertical component. And it, you know, that's the physics 30. We've put it all together with a bit of physics 20 analysis, but now to find this velocity and the angle is like stealing candy from a baby. Everybody should know how to do that. Use the Pythagorean theorem, and then use tangent to find the angle, and we're going to have our answers. So we'll just give everybody a second to find those two answers. I'm not sure if in your handout for C you have 4 blanks. You should only have 3. If there's 4, just pretend there's 3. Using inverse tan of opposite over adjacent, I get 41 degrees. So it would be 41 degrees below the horizontal. Good? This is one of these days where you're really not going to have a lot of time, but you need to make sure you know how to do these questions. If I were to take a look at this question, just briefly, we're not going to do it. You have an alpha particle, the plates are 2.6 centimeters apart, and you know the voltage. The question is, where does it land? What's the horizontal distance the alpha particle will travel? The alpha particle will do that, splat. What the question is what's that? So, if you set this up, you know this speed, you want to find this distance, and I'm going to leave this up so you can process it. We know VI is 0. What do we know? We know the voltage and the distance between the plates. We know the distance between the plates. So my thinking here is, what's preventing us from finding V is we don't know the time. But that time is this time. Now my final new thing I'm going to tell you, what in your kinematics list connects to physics 30 is the acceleration, because it's related to forces and fields. So if we can find the acceleration and we can find the time, we can answer the question. Well, How do we find the acceleration? We would need to know the force. How do we find the force? We would need to know the field. So if you organize this in your head, and some of you are going to do a calculation right now, I can see, getting the actual answer is a 2-minute thing. It really doesn't take you long. You'd have to calculate the field in this question, and then use the field and the charge of an alpha particle to find the force, then use the force and the mass of the alpha particle to find the acceleration, then use this formula here to find the time, then use this formula to find the distance. Your assignment is to work on, I'll leave this up if you want to try that one. Your assignment is to work on questions 1 to 4 on page 45, 46, and 47. I think what that means is there's actually an A and a B for these. You have a calculation and then the 2 physics principles. This is not, for the faint of heart. You're not going to sit here and look at it one time and necessarily master it. Some of you will. It's going to take some practice. So get to work. I know I left you very little time today, and I apologize. Some days are like that. Some days are